Okay. Thank you for inviting me to give this series of talks. And I was asked to make my presentation very elementary, and this might explain this indefinite number, because I would like that everybody who wishes can understand everything, and even make some computation afterwards, because I'll later explain the purpose of this work is to compare various sets of invariants obtained in different ways. But maybe I'll start with this notion of invariance. Invariance, I mean numerical invariance. So one would like to associate to algebraic varieties certain numbers in order to compare and study them. So our main subject will be a projective algebraic variety in projective space, and we'll usually assume that X is non-degenerate, which means that this n capital is chosen as the smallest possible, that X is not contained in a hyperplane. This is a very mild restriction. And then what is algebraic variety? There are many definitions. One definition is that X is defined by algebraic equations, that there are some forms vanishing on X. And even this definition, where these are forms of different degrees in the homogeneous coordinates. Even this definition is not very precise, because one can study algebraic equations, and one can study also the ideal of X, and these are different definitions. So one to give an algebraic variety means to give an ideal in the homogeneous ring of these variables, and then we can introduce various invariants defined in terms of this ideal. For example, the number of generators, the degrees of generators, and so on. And using this ideal, we can introduce the dimension. For example, there are many definitions. The definition of crude dimension, the definition of dimension as the transcendent degree of the quotient, and so on. And then, for example, from this point of view, the simplest varieties are those where there are few generators, and these are complete intersections. Simplest varieties. So what is complete intersection is that if the dimension of X is n, and we denote, and we'll use this notation, the codimension by C, then the ideal is generated by C generators. And then these are the most simple variety from algebraic point of view. But alternatively, we can study X geometrically by its geometric properties, and there are many other approaches to compute the invariance. So we can study topological invariance, analytic invariance, differential invariance, for example, the degree of X is a topological invariant, because it depends only on the topology of the ambient space. But you can study more elaborate invariants. For example, topological invariants. You can study the topological Betti numbers, and so on. For example, in the case of curves, this includes the genus, because, for example, in this case, if this gives us the degree of this curve, And in the case of non-singular curves, B1 of C is equal to 2 times the genus, although it makes sense even for singular curves. And so these are the basic invariant, 2 basic invariants of non-singular curves, the degree, genus, and the dimension of the space where it is contained. And all other invariants for curves are mostly linked with these ones. But you can study other invariants, for example, analytic invariants. You can study the Hodge numbers of X in the non-singular case. And most invariants which were studied classically are differential invariants. These are linked in particular with the canonical class. And here I'll return to this point later, but here we consider only projective varieties. But there is a third observation that we can consider abstract varieties. Traditionally, of course, all varieties were projective, but then one can ask what are the links between invariants of a given projective embedding and a different projective embedding, if the two varieties are isomorphic. And one was searching for invariants which were stable under such different embedding of varieties, and one even introduced the notion of abstract variety, which need not be contained, which are compact varieties, not necessarily contained in projective space. But soon it became evident that even to study abstract varieties, one needs to study projective varieties. And for example, here I introduced a standard invariant. For example, you can consider its self-intersection or something like this. These are standard invariants of abstract varieties, but you need not think that canonical class was introduced first and they studied such invariant starting with canonical class, because for projective varieties nowadays they define canonical class as a divisor of a differential form, but this is rather recent. Differential forms were introduced more or less by Cartan, and it's rather recent. But of course, during the 19th century, these invariants were studied, but in different terms. For example, Klopsch suggested the following procedure to study canonical class. We take a variety X like this, and we consider a general projection. So we take L be a general linear subspace here, and we project X to Pn from this space, and thus we obtain a default covering, finite covering of projective space, where D is the degree. This is obvious. And then, of course, there is some ramification, because here and here, maybe because this is a simply connected manifold projective space, and there need to be ramification, and we can study the ramification divisor. And put it in modern terms, Klopsch proved, and you can do this easily also, that the ramification divisor is equivalent to this, where H is the divisor of hyperplane section. But the difference is that this is defined, ramification divisor is defined geometrically for projective variety, and it's much more easy to define. You can visualize it. And canonical class needs more complicated abstract techniques to define it. But then if you consider different embeddings, for example, if you replace your embedding by double embedding, for example, you can easily obtain a canonical class as a difference of these two. And this was the definition they used. It's like, you see, you can, how do you define negative numbers? You can define a negative number as a couple of two positive numbers. And then you say that two couples like this are equivalent for any positive C. And then like this you can define a negative number. Simply like this they defined a canonical class. And all other invariants are of a similar nature. So there are plenty of these invariants, and the origin of all of them is in projective geometry. And so, and there actually it was shown that there are very few compact non-projective varieties, and one understands how they are constructed from projective varieties in different ways. So that in this talk I'll be concerned only with projective varieties. And you see that if we start from geometric point of view, what should be the most simple varieties of given codimension C? You know that you always have such an you always have a certain inequality for degree. That the degree always satisfies this inequality where C is the codimension. And so from this maybe topological point of view, the easiest varieties are those for which the degree is small. So X simple means the degree is small, and the simplest variety are those for which the degree is minimal. And these varieties of minimal degree were classified also a long time ago, more than a century ago. There is a classification of varieties of minimal degree, and but they are rather complicated at first glance from the algebraic point of view, because they ideal the ideal is generated by so many quadratic forms. Which is, for big dimension, this is a lot. So the ideal has a lot of generators, and it's very far from being complete intersection, because you see that it's roughly a square over 2 of the number of generators for complete intersections. But still these varieties are very simple from the point of view of geometry. Most of them are simply scrolls, rational normal scrolls over a curve, a rational curve. So the notion of being simple, you have at least two notions of being simple. These varieties may have, for example, very big canonical class, complete intersection, but the ideal is very easy to describe. These varieties have small degree and have a very simple algebraic geometric structure. They are rational in particular, but the ideal seems at first glance to be rather complicated. And so you see that these projective varieties have multiple nature. They have algebraic nature, expressed by the ideal. They have geometric nature. They have topological nature, differential nature, and this makes them interesting because you know, as soon as some object has multiple natures, then you can study the relationship, the interrelations between different natures, and you can develop a theory, an interesting theory, non-trivial theory. For example, take a human being. It has a lot of natures also. It has biological nature, physical nature, psychological nature, and even maybe it has divine nature. And then the interrelation between this is an interesting object to study. Otherwise, if it were entirely biological, for example, it wouldn't be so interesting. Or maybe we would not be interested in studying it if it didn't have a different nature. And so one maybe the reason why I was asked to make this talk is that rather recently some of the participants here, in particular Sijong Kwak and his school, have introduced some interesting invariants from the point of view of algebraic presentation of projective varieties. Some time ago, I introduced some new invariants starting from geometric representation, and there is some feeling that these invariants are somehow linked. And so I was asked to explain my work in detail so that one would be able to verify whether there is such connections, and if not, there should be some relationship. Of course, if one object admits two very different descriptions, then one is tempted to study the link between these descriptions. And so I'll start with explaining in detail the nature of my invariants that I introduced for arbitrary projective varieties, like this. And the idea is that even the presence of such a variety changes the ambient space drastically. You can imagine that this ambient projective space is a big black box, but as soon as you put a variety there, it acquires a new interesting geometric structure. And to define this structure, I must introduce the notion of joints and secant varieties. And I must say that you already, everybody learned this object, the first object that I am going to introduce, but in a simple setting, in the course of algebra. You learned, everybody starts by learning linear algebra and geometry by studying matrices, usually in square matrices, and quadratic forms, which correspond to symmetric matrices, and afterwards maybe also exterior forms which correspond to skew symmetric matrices, and so on. So, and the basic invariants of matrices are, if you have a matrix, for example, quadratic matrix or rectangular matrix, you introduce the notion of rank, and even before that, of order, for quadratic matrices at least. And what are matrices from the point of view of geometry? From the point of view, suppose that you are interested in rectangular matrices of size a plus 1 times b plus 1. You'll soon understand why I use 1 here. I add 1 here. This form vector space, but you, as usual, when we consider projective varieties, we are interested, we can identify objects which differ by a non-zero factor, and so we consider the projectivization of this vector space, which has dimension 1 less. So our matrices will be points of this projective space. But we have an additional structure here, because we now have the notion of rank, and in particular we can consider matrices of rank 1 or less. Less means that this is the zero matrix, but we have thrown out 0, the origin, because we consider the projective space. And so in this projective space we consider matrices of rank 1. And if you learned projective geometry, you know that matrices of rank 1 are called Segre product of two projective space. So now, what can we say about further terms of filtration by rank? What are matrices of rank 2? How can we represent them? And everybody who passed the exam about matrices can tell that any matrix of rank 2 is a sum of two matrices of rank 1. And so we should somehow add points of this variety to points of this variety, but before identification in projective space. So geometrically, this means that we can take two matrices x1, x0 maybe, and x1 here, which correspond to two matrices of rank 1, and we should join them by line. And you can see that before identification, that means that we can take arbitrary linear combinations. So we have 2 points here, we join them by line, and then we see that these two matrices have rank 1, and the other points of this line correspond to matrices of rank 2. And we can proceed further. We can take 3 matrices of rank 1, consider the plane, the plane that they span, and then these 3 lines will consist of matrices of rank at most 2, and the other matrices in this plane will have rank 3. And you know also that this representation as a sum of matrices of rank 1 is not unique in principle. And then it is studied to what extent it isn't unique. And we would like to make a similar argument for arbitrary variety X, not just for Segre variety. But before passing to this, I'll consider a special case which is mostly studied in the university, the case when B is equal to R. So the case of quadratic matrices. And in this case, there is a special subcase which is studied very extensively in the course of algebra. You can consider not necessarily all matrices, but special matrices. And the most interesting case is symmetric matrices. And symmetric matrices, in this interpretation, they of course form a subspace and even a linear subspace, because each relation of the type like this, or maybe M, is a linear relation. And this means that we cut this space by certain hyperplanes, and eventually we consider the intersection we consider the linear subspace defined by all this equation, and on the level of rank 1 matrices we get who knows what. What is the subvariety here made by symmetric matrices? Who can answer this question? And well, then I answer it.
7.
Yeah. So we had this variety in here. No. Yes. And we consider its intersection with a linear subspace, which defined by equality of terms symmetric with respect to diagonal. And this means that here we have also points xy, and you can express this condition by x equal to y, which means a diagonal. And this diagonal is known to algebraic geometers as the Veronese variety. So it has dimension, if we speak about matrices, only about matrices of rank 1, then this variety has dimension half of the dimension of this Segre variety. It's obtained from Segre variety by intersecting it with the diagonal, which is cut by a linear space. And this is the Veronese variety, second Veronese variety, obtained by embedding PA by all monomials of degree 2. So you take a PA with these coordinates, and you consider the embedding defined by all the products. But of course, since we can only consider this product, because otherwise we get the same thing, and then we obtain this embedding. What is interesting is that the geometric interpretation is that when we consider linear sections, hyperplane section of this variety, there are these Veronese images of the quadrics in the original space. So instead of studying quadric hypersurfaces, we can study hyperplane sections of this Veronese variety. And now again we can consider lines through 2 points, so planes through 3 points, and so on. And if finally we get the ambient space, but here we get the ambient space after summing up a points here. So any point, and we get the following theorem, which is proved in the course of algebra, that if we take a points, any point in the ambient space, it can be expressed as a sum of contained in a span of a points of the Veronese surface. And in the course of algebra, this theorem is known in the following form. Take a complex. We'll speak mostly about complex varieties, although much can be done for varieties of arbitrary field. Take any quadric of a variables, or a plus 1 variable here in projective terms, then Q has the form where these are linear forms. Some of them may be 0. Which, said differently, this means that any quadratic form can be represented as a sum of linear forms whose number is at most equal to the dimension of the space plus 1, projective dimension plus 1. And this is, a classical theorem about the reduction of quadratic form to a sum of squares. But this is valid over algebraically closed field. If the field is not algebraically closed, then you need some coefficients, but you all know this. And then it's an interesting question, which is also studied. How many ways are to represent this quadratic in as a sum of squares? And you can answer this question, and we'll return to this question in a general setting. Maybe here I should also mention that this question is a special case of the Waring problem. And the general, it's a classical problem of dating back maybe, I don't know, almost 300 years maybe. And it asked, it was first posed for natural numbers. It was known even at this time that any number, any natural number k is a sum of two squares, 4 squares, at most 4 squares. Sometimes less, sometimes, but never more. Any natural number can be represented as a sum of 4 squares, at most 4 squares. And then he posed a problem. Suppose that we would like to represent it as a sum of cubes. How many cubes do we need? Of course, we can do this because we can take, for example, number 1 and take k times number 1. But it turned out that you need much less, 9 is, I suppose. And then how many d-quadrates, 4th powers do you need, and so on. And this, there are some bounds, there are some conjectures, but still I think that we still don't know the exact answer. But then much later, in around 100 years ago, one asked a similar problem for forms. So suppose we have a form of degree d, in these variables in our notation, and we would like to compute the number of forms, linear forms, or maybe starting with 0 maybe it's better. You can ask how many forms you need to represent any form. There are two possible equations. First, any form as a sum of at most r plus 1 square, r plus 1 this power. And so here is the answer of this for quadratic forms, which is taught at the university course of algebra. And second formulation is do this for general forms. It turns out that for general forms, general means a dense open subset in any sense, in Zariski says so, in topological sense. And it turns out that to represent a general form, you need generally less forms. And these numbers are interesting to compute. And we'll return to what we can say about this later. But interestingly, usually there are some exceptional cases, but the most interesting exception is given by quadrics. That's why one of the reasons why quadrics are so important. But now I pass to the general definition of analogues of ranks and order for any variety. So here we gave definition for Segre variety. Here I recall the definition for Veronese variety, and now I would like to do something similar for arbitrary variety. And so I already explained what should be done. So given a variety X, we should first consider this corresponds to matrices of rank 1, I recall. Then to construct an analog of matrices of rank 2, we should join pairs of pointers